Okay guys, what we're going to have a look at today then is the reactivity of the group 7 elements and how that reactivity changes as we descend the group. So the first thing that I would advise you to do is get yourself a periodic table, because clearly if we're looking at group 7, that's exactly what you're going to need. So we're going to be looking at these elements here, which I have drawn the oval around in white. We're going to look at how the reactivity of those elements changes as we go down the group. So already this year you should have looked at how the reactivity of group 7 elements changes. So the group 7 elements really being over here from lithium through to sodium and potassium. Okay, you may well have looked at the videos on the screen of rubidium and cesium, but you don't have to deal directly with the chemistry of those. And if you remember, the reactivity of those elements increases as we descend the group, and the reasons for those have been covered in another video. And those are, of course, the group 1 metals, okay, commonly known as the alkali metals. Then what we need to look at are group 7, okay, so group 7 also, as you should know, referred to as the halogens, and we will take a look at fluorine, chlorine, bromine, and the trend then down to iodine and acetine. Really is just the same trend, but if we can deal with fluorine, chlorine and bromine, that will do us fine. So the first thing we need to ask ourselves is, well, okay, what actually happens when these elements react? And we should know this already. We should know that they are non-metals. Okay, so the group 7s are of course non-metals. We should know therefore that if they're non-metals, what they will do when they react is they will gain electrons. The reason why they do this is to get a full outer shell of electrons, or in other words, to get 8 electrons in their outer shell, or to get a full octet of electrons. So how do they do that? Well, if we take a look at fluorine, fluorine has an atomic number of 9, so therefore it has an electron configuration of 2, 7. Chlorine has an atomic number of 17, and as we go down the group we introduce an extra shell, and therefore it is 2, 8, 7. So when they react, the chlorine will gain an electron, go to 288, and will become a 1 minus ion, now called a chloride ion, not a chlorine ion. Note the D. And the same will happen up here with the fluorine, which will turn to a 1 minus ion, which is a fluoride, and it will go to 2,8. So when both react, they both gain 1 electron, okay, whether it's the chlorine gaining it or whether it's the fluorine gaining it. So therefore, whichever one is able to attract that electron most strongly is the one which is going to be the more reactive. So the next thing we need to ask ourselves is, okay, well, if there's a fight between chlorine and fluorine over an electron, who's going to win the fight? Because whoever wins the battle for the electron is going to be the more reactive of the two elements. So then we need to ask ourselves, well, what is it within fluorine and chlorine which actually attracts the electron? Well, hopefully you know by now it is, of course, the nucleus. Okay, well, so therefore let's say that the top atom that I've drawn there is fluorine and the bottom one is chlorine, and we've got an electron here and they're battling over the electron. So we know that fluorine has an electron configuration of 1, 2, and then we have, of course, 7 electrons in the outer shell. We know that chlorine has got 2, and then it has 8, and then I'm going to go over my other chlorine here. I'll just make these electrons in a slightly different color because they'll be a little bit more easy to see. So we have 2, we have pairs of electrons, 4 of them of course, to make up our 8 electrons here, And then we have 3 pairs of electrons in the outer shell of the chlorine, and of course we have 1 electron on its own. So what is it that is going to attract the electron to the fluorine, and what is it that's going to attract the electron to the chlorine? Well, it is of course this part of the atom in here, okay, which is of course the nucleus. Now specifically within the nucleus it's got to be the protons, and the reason why is because the protons are the negative particles. Okay, there are of course neutrons in the nucleus, but neutrons have no overall electrical charge, so therefore they're not going to attract electrons. No, we need to delve a little bit deeper then into what's going on within fluorine, and we learned earlier that fluorine had an atomic number of 9, whereas chlorine has an atomic number of 17. So what that means is that fluorine will have 9 protons in its nucleus, okay, and chlorine will have 17 protons in its nucleus. So based on that, we would imagine therefore that chlorine would be able to win the battle for this yellow circled electron, because it has 17 positive charge. We just write the 17 in there, we write the 9 in there, but there's another factor at play here which is battling against the fact that chlorine has more electrons than the fluorine. So maybe you might want to pause the video for a little second and see if you can work out what that is. So that factor is the number of shells then. So, and therefore the distance between the nucleus and this outer shell, I just label it D, and again I label it D1 here. So whilst chlorine does indeed have more protons, it's the distance from the protons here, from the nucleus to this outer shell, that means that in actual fact chlorine's attraction for this electron is less than fluorine's attraction for that electron. So therefore, if there's a battle, okay, for the electron, fluorine will win that battle. And the reason is not because chlorine has more protons than fluorine, but it's the fact that even though fluorine has fewer protons than bromine in its nucleus, the distance between that nucleus and the electron that it's trying to attract is less, and therefore this electron will be taken up by the fluorine. Okay, so therefore we would say that in terms of reactivity, fluorine is more reactive than chlorine, and we would say exactly the same again then if we went further down to bromine. The same argument would be continued, and therefore bromine, because it has even more shells than chlorine, would be less reactive than the chlorine. So what we're seeing here then, if you think about it, is a trend in reactivity of the non-metals, the group 7 non-metals, which is exactly the opposite to the trend in reactivity of the group 1 metals. So hopefully we can remember that when we had the group 1 metals, as we went down the group, the reactivity, as I'm trying to show here with this fattening arrow, increased, but as we go up the group with our group 7 non-metals, the reactivity increases. So the trend is opposite. What's going on is opposite, because essentially our group 7 non-metals have to gain electrons and become negative ions to gain their full outer shell, whereas our group 1 metals had to lose an electron to gain a full octet or a full outer shell of electrons. Okay, that's more than enough information for you to be able to answer any GCSE question which comes your way with regards to the reactivity of group 7 elements. I'll do another video on displacement reactions based on this reactivity, which will also allow us to further prove this theory of the reason behind reactivity of group 7 elements. I hope that helped.